All right, so in the second problem of the homework, water was boiling because they had this electric heater, right? That heating element. And so the water is sitting at 250 degree Fahrenheit, and the surface is sitting at 280 degree Fahrenheit. That's TS. And this is T saturation. So see, this is the moment when now the bubbles, any bubbles that will generate, will actually manage to survive all the way till the end. When you start the boiling, this wasn't the case. The water was not at 250 Fahrenheit, probably it was at 70 degree Fahrenheit. And the heating element initially wouldn't make any bubbles because he couldn't sustain a temperature higher than T saturation because he was surrounded by very cold water. And he eventually started heating the water around him, and because he really just gives you Q. The resistance inside does not control the temperature. The resistance, the electric resistance inside, just basically send Q, right? Heat flux need to come out, and that heat flux will determine, based on what's the cooling mechanism around it, how hot it will get to manage to send the same Q. So imagine this is 1 kilowatt heater. Every second, 1,000 joule need to go into the water. The water is at 70. What's the mechanism of the heating? Natural convection of our horizontal cylinder. There is a certain H, there is a certain area. And that 1,000 watt, in order to leave by natural convection, it requires TS to be, I don't know, 100. So the TS will set at 100. So what will happen? The water that's being heated by natural convection will not be at 70 anymore. After a few seconds, the water will be at 75, will be at 80, will be at 90. The 1,000 still need to get out. So now the 1,000 will take, because it's still the mechanism of natural convection, it's not enough that you be at 100 so that you just disperse this 1,000 into 90 degree Fahrenheit water. So as the water temperature get up, the TS also get up. Now once he go up above the T saturation, now he has a chance to generate something else besides just natural convection. He will start making boiling, right? So 5 degree above T saturation, he will start making nuclear boiling. And you will get higher and higher. 30 degree above T saturation. And now he can actually generate more than nuclear boiling. He actually can go to the maximum heat flux, or he can start going down to film boiling even. So what I'm saying in those problems, the TS is controlled by the Q. Right? The Q say, I have to get out, otherwise I will get hot. That's what really happened. That if you don't take the 1,000 out by whatever mechanism you have, the surface will get hotter. The heater is not cool enough. And that's what happened in nuclear accident. In nuclear accident, there are the cylinder. The cylinder is not cooled by electric current, but they are cooled by radiation. That radiation rate is controlled by how many fission is happening, how many atoms are splitting. And there are certain Q that need to get out. You have water around us, all right, we will keep you at cool temperature. That's enough to maintain the safety of that nuclear reactor. But if the water is not there, why? Something happened, the water is out of the reactor. It's just surrounded by air. Well, the air natural convection is not the same as the boiling mechanism that was taking a lot of latent heat. So as a result, there is not enough mechanism that will make that natural convection enough to disperse that Q. So the element will get hotter and hotter, right? Until what? Until his radiation and his natural convection at this high temperature would be enough to send away that Q. And unfortunately, that could happen at very high temperature, that temperature will melt everything around the rods, and therefore there is no even mechanism to bring any more fresh air or any more seawater to cool it, or any more nuclear rod and safety rod that will come in and try to kill the radiation. Right? So the Q control the TS, and not just like in those problems where I give you what is the TS. All right? So we have the dimension. So L is given, it's 2 feet, and D is given, it's 0.25 inch, and it's nickel plated heating. So we know we can get the CSF from that table. Remember, there is a table that this is basically based on the material and the manufacturing technique. We can actually tell what is that constant. All right, and please find the rate of evaporation in pound per hour. Assume steady state nuclear boiling. So and as a hint, the properties also were given for us at 250. So don't get used to this. Maybe I will just ask you to actually check the property yourself. So familiarize yourself with the tables in the textbook. Find out where are the tables for water, where is the table for at the appendix. All right. So the tables were all the property were given to us: raw liquid at T saturation, raw vapor at T saturation, sigma, the Prandtl of the liquid, the HFG, the mu were given, the CP were given. Was given as well. Okay. And so all is needed is CSF. So for nickel plated, the CSF was 0.006, and the N was 1 because it's water. Right. And now, should I use this or should I use this? There is 2 Q that you're responsible for in this textbook. Q for nuclear boiling and Q for maximum heat flux. And the 2 formulas are a little bit different.
This is boiling.
Well, this is also, let me put it in red. This is also boiling. What do you mean boiling? So Brandon is saying, he said the water is boiling, or it's obvious to us that water is boiling. So this doesn't answer my question. My question is, for boiling, there is this formula for this part of the curve. It's called nuclear boiling, when the water is just leaving a bunch of separate bubbles. They don't organize themselves. They don't start shooting up in jets. And there is this point where, at this point actually, you approach this point gradually. So what I'm saying is that near the tip over here, things are screwed up. It's not really nuclear boiling, it's not the maximum heat flux yet. It's kind of transition toward this point. So there is Q here and there is Q for this range. Yes?
So we're supposed to use nuclear boiling for the excess of anywhere from 5 to 30. So we use.
So it's actually sharply 30. So you think we should go for nuclear boiling, right?
Yeah.
Because it's within that range, right? So assume nuclear boiling. The Q dot then would become this here, mu L, HFG, and you got G, rho L minus rho vapor, sigma, 1/2 CP L, TS minus C saturation, CSF, HFG, Prandtl, L, N, the whole thing here to power 3. And you got all those numbers, including the CSF and the N that you just came up with from the table. And so this become, and since the units on the hand, they were all given to us in English units, so let's just go ahead and use it. And just make sure that there is no inches. Right? So what I'm saying is that you should stick to pound feet, unless they cancel out. If you see inch over inch, then that's okay, for example. Right? So the end result is 3,475,221 BTU per hour feet square. And so that's the Q. He wants to find the rate of evaporation in pound per hour. So how can we get m dot evaporation? How many kilogram per second are evaporating? Anyone? So you'd like to find how many pound per hour or how many kilogram per second of water turning into vapor. That's the rate of evaporation. How do you get that? Right. So Jose is saying that joule per second that the heater give is being converted to latent heat that turn the water bubbles, basically, or create the water bubble, right? So the Q dot, which is this Q dot flux multiplied by the surface area of the heater, is the same as m dot HFG, right? Those joule per second are the same as those joule per second. That's the mechanism of sending the heat into the water, is basically by turning the liquid into vapor. Right? So Q dot multiplied by the area, it become 133.3 10 to the power 3 watt, and or actually we can also do it in BTU per hour. So it's 454,905 BTU per hour, and that same Q dot again is m dot HFG, or basically m dot multiplied by the 946 BTU per pound mass. So this is BTU per hour, and this is BTU per pound mass. This will have to be pound mass per hour, and it is 481 pound mass per hour. And so this number was worth half a point, and this formula was worth half a point. And this was worth 1 point. And this was worth the rest. So questions?